All right, welcome to The Explainer. Today we're going to crack the code that powers, well, everything in our digital lives. We're going to find out how computers can do all the amazing things they do with just two simple numbers, 0 and 1.
Okay, so let's just kick things off with one single foundational fact. Everything. And when I say everything, I mean it. From the words in an email, to your favorite songs, to the most complex video games, is all stored inside a computer as just a long, long string of zeros and ones.
So yeah, that's the big question, right? It seems kind of like magic. How does that even work? But trust me, by the end of this, you'll see it's all based on a few really simple, elegant rules. So let's break it all down.
To get our heads around the computer's language, we've actually got to start with something we use every single day. Something we don't even think about. Our own base 10 number system. Think of this as our Rosetta Stone for figuring out binary.
You know, the secret sauce here is this really powerful idea called a positional number system. And it's way simpler than it sounds. The whole idea is that a digit's value isn't just about what number it is, but where it sits in the line. Its position is what gives it its real power.
Let's just take a regular number, say 5281, and break it down. That 1 all the way on the right, that's just 1. Simple enough. But the 8 right next to it, that's not just an 8, it's 8 tens. And the 2 is 200s. And the 5, you guessed it, 5,000s. See? Each spot has its own weight, its own power of 10.
And that right there, that's the key. The crucial point is that once you get that a number's value comes from the digit times its position's weight, well, you've basically unlocked the secret to understanding any number system. And that includes the one computers use.
All right, so now that we have that key, let's use it to unlock the computer's native language, binary. It's just a base 2 system. Same exact rules, just a different base.
Okay, check this out, because this is where it all clicks. In our normal, everyday decimal system, we count up to 9, and then what? We're out of symbols. So we stick a 1 in a new spot to the left and start over at 0, making 10. Well, binary does the exact same thing. It just runs out of symbols a whole lot faster. You go 0, then 1, and bam, you're out. Time to roll over to 10.
And that's why binary numbers always look like these super long, kind of intimidating strings of digits. They're playing by the same rules we are, but since they only have two building blocks, 0 and 1, they just need way more spaces to say the same thing.
And you can really see the pattern here. 0 is just 0. 1 is 1. Then, whoops, out of digits, so 2 becomes 1, 0. 3 is 1, 1. To get to 4, we need another new column, so it becomes 1, 0, 0. Each new spot you add to the left is just the next power of 2. You have the 1's place, the 2's place, the 4's place, the 8's place, and on and on.
And that right there leads us to a word you have absolutely heard before. Every single one of those binary digits, each 0 or 1, is called a bit. It's just short for binary digit. Think of it as the tiniest possible piece of information, the atom of the digital universe.
Okay, so let's put this into practice. How do we actually read a binary number like 110, 101? Well, we just use that same positional logic. We've got a 1 in the 1's place, nothing in the 2's place, a 1 in the 4's place, nothing in the 8's, a 1 in the 16's place, and a 1 in the 32's place. You just add them all up, and what do you get? 53. See, it's not some crazy new number, it's just a different way to write 53.
So you can probably imagine staring at pages and pages of ones and zeros would drive anyone nuts, even programmers. So they came up with a really clever shorthand to make these long binary numbers way easier for us humans to handle. And that shortcut is called hexadecimal, or just hex for short. It's a base 16 system. Now, to get 16 different symbols, it uses our normal numbers, 0 through 9, and then it just borrows the letters A through F to represent the values 10 all the way up to 15.
So why is this so useful? Well, the real magic is that switching between binary and hex is ridiculously easy. Let's take a look at this 8-bit number and see how it works.
The whole trick is you just split the binary number into little groups of 4 bits. Now, why 4? Well, because a 4-bit number can represent exactly 16 different values, from 0 to 15. That's 2 to the power of 4. And that maps perfectly onto a single one of our hexadecimal digits. And the best part is, you don't even have to do any math in your head. You just use a simple lookup table, like this one. Every single possible 4-bit combo has a direct 1-to-1 translation to a hex digit. It's that simple. So if we look back at our number, that first chunk, 1,000, is just 8.
The second chunk, 1100, is the number 12, which in hex is C. So that long, clunky binary string becomes the nice, clean 8C. It's just so much more compact and way easier for a person to read without making mistakes.
All right, so we figured out numbers. That's a huge step. But what about words? What about all the letters and symbols that fill up our screens? Well, that's the final piece of the puzzle.
Right, because that's the obvious next question. This is all great for numbers, but how can a bunch of zeros and ones possibly represent the letter A or a dollar sign? How does a computer know the difference between the number 65 and the letter A?
The answer is just another code, another layer of translation. It's a universal agreement called ASCII. And you can think of it like a giant dictionary that just assigns a unique number to every single character you can type on a keyboard. Uppercase, lowercase, punctuation, you name it.
And this is where the magic really happens. A computer doesn't actually store the word deer. No, it stores a sequence of numbers. It sees the ASCII chart and knows that D is just the number 68, which it keeps in binary. E is 101, and so on. All the software on your computer does is look up these numbers in the ASCII table and draw the right letters on the screen for you to see.
Now, ASCII was a brilliant start, but it was pretty limited, mostly just for English characters. So today, most of our systems use something called Unicode. It works on the exact same principle, assigning numbers to characters, but it uses a much bigger set of numbers to represent symbols from pretty much every language on Earth.
So when you boil it all down, what's the big takeaway? It's that this incredible, mind-boggling complexity, I mean everything from a simple text to a massive online game, is all built on this ridiculously simple foundation. Just on and off switches, a few rules about position, and a couple of translation tables. And it kind of makes you wonder, right? If our entire digital world can be built from these simple, logical rules, what else can be?